Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. This is Linear Algebra 1. We're doing Chapter 4, which is the arithmetic vector space Rn. This section is 4.2, which is going to be linear independent span and basis, and then parasitically, essentially, the notion of dimension. Really the question when they ask you what's the dimension of this thing, the dimension we'll find out is the number of basis vectors in any basis for that vector space. So when you ask about what dimension is, really you're asking the question, find me a basis and count how many guys you have in there, and that's what dimension is going to be. So this lecture, what are we going to specifically do? We're going to do linear independence and spanning, and if you are both linearly independent and span a space, then you are a basis of that space, and the number of elements in that basis is the dimension of the space. So we're going to go over the generalization of basis for a vector space Rn, and then we'll get the notion of dimension along the way. Let's do that. Now I'm ready. Read the cup, people, read the cup. Get the sign. Everything I do in these videos will be potentially fair game for a test. What does it say? I don't even remember. This is a tautologically false thing. Everything that I say will be on the exam. That means including the things I'm saying right now will be actually written on the exam. If you think about it, that could never be true. So, don't worry. Most of what I say will be on the exam. Most of what I say. Definition. Consider the set of vectors, some set of vectors in dimension n. So, now, how do I know I'm in Rn? This guy is the number of coordinates these guys all have. They all have coordinates. They're column vectors. If I'm in dimension n, that means they have n coordinates. But now I have k of them. We're going to do this eventually. There's going to be Goldilocks land. There'll be whether the number of vectors is equal to the dimension I'm in, less than the dimension I'm in, or larger than the dimension I'm in. And two of those cases, you can never be a basis. One of them, it's anti-Goldilocks land, again, where it's a if and only if. We need these conditions for what a basis is. The two horrible conditions to generalize this now are this set of vectors in Rn spans a single vector, first of all, if, unfortunately, that horrible word span means linear combination. I don't know why they didn't just incorporate this as the term. These guys linearly again, that's why they were like, okay, span. But these vectors span a single vector x if you can write it as a linear combination. That's all span means. I need to write x as a linear combination of those other vectors. So if I can write it that way, we say that x is in the span of those vectors, or those vectors span a single vector. And then generalizing in particular, if we want to span the whole space Rn, that means every vector in Rn has to be written as the span of those vectors, which means if I take an arbitrary vector in Rn, then I can write it as this linear combination, which coincidentally means that that vector is now in the span of those vectors, which means those two sets are equal, and we span space. So also recall that the span of vectors is all possible linear combinations. So this is the span business. You can also look back to one of our previous videos when we did this for basis for 1 dimension, 2 dimensions, and 3 dimensions. We went over this horrible notion of span and independence. Now what we're going to get is essentially this is what we're going to do is a basis is going to be, you have to be a collection of vectors which spans all of space and are linearly independent in space. Why do I want those conditions, whatever those conditions are? First of all, I want those because that says that will be a basis, and then I can describe uniquely every single vector in that vector space with just those n basis vectors. And this is why we want a basis of space, because then every object in that space can be described uniquely with our basis vectors. And then we can do all kinds of crazy things and uniquely determine their images under linear transformations in the next chapter. If you know what a basis is, you know how the basis vectors move. Because of the properties of linear transformations, you'll know what the image looks like entirely. So this is extremely useful. We want a basis. But what is the basis? A basis is a way of uniquely describing every vector in the vector space with your basis vectors. That's what we want. How do we get it? You have to have spanning the whole space, and you have to have linear independence in that space. What are they again? Vectors span Rn if and only if every vector in Rn can be written as a linear combination of those guys. So what that says is, I want to describe everybody in Rn with these vectors. I would like it to be the condition that they span, because then I can actually look at, or I describe them at least one way. So spanning says that you can actually describe them with those vectors, x. And then what I want linear independence is saying none of these vectors depend on each other linearly, so you can't rearrange anything and get more than one description. This will be the only description. So linear spanning says that you can get a description with those vectors of x, and linear independence is going to guarantee that that description is unique. And if you have both of these conditions, this is what a basis of a vector space is. So what is linear independence? It's this horrible conditional in the conditional. If you have this conditional statement, if 0 is in the span of these guys, the only way you can get that is if all of those coefficients were 0. And so this condition says that if you get these vectors are a linear combination of 0, then the only solution to this homogeneous system of equations you're going to see is the unique trivial solution. If I have this condition, then we call them linearly independent. So if you have this if-then, then they're linearly independent. And that bothers everybody intellectually at first. So these are the two horrible definitions of span and linear independence. And then we're going to get the notion of basis and dimension out of this scenario. Let's do that next. All right. Theorem, which is essentially 3 properties about independence, linear independence. The first one says that any set containing the 0 vector is always linearly. Oh, first of all, what is linear dependence? Not independent. So you're going to see that this is the most important condition for dependent. What linear dependence by definition says, I'll get into it when I prove this anyways, but it says that if you have a set of vectors which are dependent, that means you can write them as a 0 as a linear combination of them, and at least one of those coefficients is not 0. Why is adding the 0 vector into a set of vectors always going to give me linear dependence? We'll see in a second. The other condition is going to be if you have a set of vectors which already has a subset which is linearly dependent, the larger set by adding more vectors in there isn't going to magically create linear independence. So if the smaller set was already dependent, by throwing a few more vectors in there is never going to magically create dependence. So if you have a subset which is linearly dependent, the set itself is also linearly dependent. And that one doesn't get used that much. You don't have to worry about it. This is the one we're definitely going to use quite a bit. A set of vectors is linearly independent. A set of vectors is linearly dependent if and only if one of the vectors is a linear combination of the others. That's independent is specifically, I don't want to be able to write the one as a combination of the others. That's where we're going to get uniqueness from. All right, so let's prove these 3 things then. Let's see how that goes. Actually, let's start off with, and then I'll rewrite the other ones. So let's just kill these 2. How do we prove this? Proof. First, you write out the word proof. There. Step 1. Proof goes here. Done. That's how philosophers prove things. Those are the details I don't have to know, but we assume it can be. Someone showed it. Anyways, we're mathematicians, not philosophers, so we have to prove it. What is it going to say? If the so here's the set, and then you can't picture it. The semantics or the rhetoric, you're like, I don't see it. So there's S, some set. Let's just suppose 0's in there, and then we have a bunch of other guys. So I've thrown 0 into this set of vectors. As soon as it's in there, why does that claim as dependent? Well, first of all, what that says is I'm going to cleverly do this. I'm going to write 1 times 0 plus 0 times v1 plus dot 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 plus 0 times vk, and that equals the 0 vector. And why is that? But 1 does not equal 0. So this says I have a linear combination of these vectors which equals the 0 vector, but at least one of the coefficients is not 0, therefore dependent. So S is dependent. So if S has the 0 vector in there, then I can do this clever business where I just pick, with 0's in there, I pick a coefficient which is non-zero. 1 is the nice enough number. So 1 is not 0, and I can write these vectors as a linear combination, or I can write 0 as a combination of these vectors where not all of them are 0. Therefore, that's our definition of dependence, and now we're done. That one wasn't so bad. If 0's in there, you can't be independent. So what does that really say? A basis can never have the 0 vector in it, because you will automatically ruin linear independence. For the second one, what we're saying is if we had a subset which was linearly dependent, then the entire set is dependent. So here's S. I've cleverly phrased it slightly differently. What I'm going to say is, suppose this is the subset where these are dependent. And then I don't know about the other guys, but I've jammed in these extra vectors up to k, but these guys are already dependent. Well, what does that say? That tells me that I can write alpha 1 v1 plus dot 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 plus alpha r vr equals 0, and at least one of some alpha I in there is not 0. I don't know which one, but I is between 1 and r. Now just do the other same trick I used for the reverse for the 0 guys. Just make all of these coefficients zeros and write out a new linear combination. Well, that says then alpha 1 v1 plus dot dot plus alpha r vr plus 0 times vr plus 1 plus 0 times vk is equal to 0. The vector 0, not the number 0. The lines are important. What does that say? Where we still know some alpha I is not 0. What does that say? That says S is dependent. And since he's trying to do it anyways, this kitty's trying to mess with all the props in the background. I know, what's up there? Linear independence, so fancy. So if you have a set which already has a subset which is dependent, you can just cleverly do this trick where adding a bunch more vectors in wasn't going to magically make it independent. It's still going to be dependent. And I know. What's our last condition? 3 was an if and only if the set S is dependent, if and only if one vector is a linear combination of the others. Who are the others? Not the Nicole Kidman one, I don't know what it is, but it's the other vectors. I'll show you what that means in a second. So Dr. Solomonovich in his textbook does this where this is actually a biconditional statement, and when you have an A if and only if B, when you actually want to prove that that is tautologically true to the statement A implies B and B implies A. That's why it's a biconditional. We have two conditionals, and if they're both true, we say if and only if. So Mark goes through this and says, assume this, and then I'll show this one, and then he does the reverse and shows both of those. I'm just going to be lazy and try to use an if and only if arrow in each step, and we'll see if that works out. If not, I'll switch back to doing both conditionals. So if S is dependent, what does that mean? Well, S, first of all, was some set of vectors v1 to vk, say. If it's dependent, that says if and only if, because we know it's dependent, that's if and only if alpha 1 v1 plus dot 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 plus alpha k vk equals 0, and alpha I, say, is not 0. There's at least one alpha which is non-zero. Well, what that cleverly says is, I'm going to write this as an if and only if. Let's write this as alpha 1, so v1, I'll show you what I'm going to do. I'm going to do index nightmare just to show you. So alpha I is the guy who's not 0. So I'm going to do alpha I minus 1 vi minus 1 plus alpha I vi plus alpha I plus 1 vi plus 1 plus alpha k vk. This is the guy who's non-zero that I know. So what I'm going to do is solve for this one in terms of the other ones. And so this guy's coefficient is non-zero. So I'm going to write this as if and only if alpha I vi equals negative alpha 1 v1 plus dot 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 alpha I minus 1 vi minus 1 plus alpha I plus 1 vi plus 1 plus dot 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 plus alpha k vk. What does that say? He's not 0, which is important, so I can divide by him. So if and only if vi is equal to negative alpha 1 over alpha I times v1 plus dot 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 plus negative alpha k over alpha I times vk, which says this vector is a combination of the other vectors. And that was if and only if, if and only if, if and only if, if and only if, if and only if. So I was lazy, but this is dependent if and only if I can write one of the vectors as a linear combination of the other vectors. This is why we called it dependence. This vector depends linearly on these vectors. Now let's get to what a basis and dimension are, right? Yes. All right, so definition, a basis B of Rn, remember B is going to be a collection of vectors v1 to vn. It's going to be a basis of Rn if it has two properties now. It has to be linearly independent and span all of Rn. So those will be the two things we get. Luckily, unbeknownst to you right now, but once we get rid of all of this mumbo-jumbo theoretic stuff, how are we going to actually answer the question of, I'm going to give you vectors and be like, are they independent? Are they spanning? Are they a basis? And so we're going to have to go through all the scenarios, but we're going to be able to use chapter 1 and phrase this as an augmented homogeneous system, and then augment a matrix and row reduce. But now when we get to REF, not only do we have to decide whether we have one solution, no solution, or infinitely many solutions, I have to use that three-pronged scenario to answer the binary question of yes or no to independence, yes or no to span, or yes or no to basis. So then that's where we're going to push that all together to use linear algebra to answer the question of these horrible things. Are they independent? Are they spanning? Are they a basis? In the Goldilocks land, it'll be if and only if, and I'll show you how to use the matrices to get these answers. Just a second. For now, this is what a basis is. You have to be linearly independent and span space. Again, what does that do? These vectors B span all of Rn, which means every vector in Rn can be written, or I can describe every vector in Rn with those guys. So that's what I wanted to do. But I don't want there to be choice. So independence guarantees that none of those other vectors can be written as combinations of each other, because that only happens when you're dependent. And so if they're independent, I can't describe any of those vectors in terms of each other. So the description, I can describe everybody and it will be unique. This is what a basis is. A basis gives us a way of uniquely describing every vector in that space with just the dimension, or n guys. So what is the dimension? Here's Dr. Solomonovic's more rigorous version of what dimension is, which is probably better than mine, but I'm lazy and I want the students to have an easier way to remember it. So the maximal number of linearly independent vectors in a vector space is the dimension of that space. So for 2 space, what was it? Any 2 non-collinear vectors are actually linearly independent. So the maximum number of linearly independent vectors in the plane is 2. So a plane is 2-dimensional. The maximum number of linearly independent vectors in 3 space is 3. So R3 is 3-dimensional. When you get into more abstract ones, why are the set of all 2x2 matrices 4-dimensional? When you ask these questions and you're trying to think about it that way, the real question you want is my remark. When I ask you what the dimension of something is, you need to find a basis and count how many elements are in there. That's what the dimension of your space is. So I can't really quite get at that before I get at Mark's definition. He says the dimension, which we're going to denote doing V, is the maximum number of linearly independent vectors that you can get in that space. To rephrase and cheat a little bit, theorem, given a vector space V, all bases have the same number of vectors in them, and of course they'll be linearly, a basis means that they're linearly independent. So using this, essentially, I can rephrase a little bit and remark. For Mark Solomonovich, I couldn't help myself. But we're going to remark and get a slightly better way of viewing dimension. We can now define dimension of a vector space as the number of elements in any basis, because that'll be the maximum number of linearly independent vectors. They all have the same size. So when I ask you what the dimension of something is, what I'm really asking you to do is find the basis for them and then count how many guys are in there. That's what dimension is. Let's do at least an example of that scenario. No, wait, I have to do one more theory type business, then we'll do an example. All right, before we move any further, what I'm going to do is actually prove the fact that what I kept saying is, why do I want a basis? Because the description of every vector in that basis is unique then. So what they're saying is, if you have a vector space V and a basis B that you have, which you guaranteed it's a basis, so it's already linear independent and spans that vector space, if I take any vector in that space, I can get a unique description with that basis. So what do they mean by that? Proof. How am I going to do that? Well, let B equal, say, some vectors, V1 to Vk. If that's my basis, and technically if it's n-dimensional, it's going to be n, because there has to be exactly n of them, whatever. Here's my basis. Then what I'm saying is, suppose I have some other vector x, and I can describe the coordinates, or how do you get coordinates of a vector? The coefficients and the linear combinations. So that's what we're saying is, assume I have 2. How do I show uniqueness? I'm going to say, well, suppose x has 2 different combinations, alpha 1 v1 plus dot 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 plus alpha k vk, and then say I can also write x as beta 1 v1 plus beta k vk. Suppose I have two different ways of describing them as a linear combination. Then what do I have to do? Knowing the fact that I have the information that this is a basis, so it's linearly in spans, I have to show that alpha 1 equals beta 1 and alpha k equals beta k. How am I going to do that? Well, I'm going to use Hypatia's transitivity of equality. If two things are equal to a third thing, they themselves are equal. So these two things are both equal to x, so I'm going to set them equal to each other. So that immediately says that alpha 1 v1 plus dot dot plus alpha k vk is equal to x, which is also equal to beta 1 v1 plus dot 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 plus beta k vk. And now the extremely clever thing is it doesn't matter, but classically we move them to the left. We'll follow Beyonce to the left, to the left. So move everything to the left, and what are we going to get? The zero vector. I'm allowed to additively inverse all of these vectors, so I can create their negative. When I add those negatives, it creates a zero vector. When I move them all over, I'm going to get alpha 1 minus beta 1 v1 plus dot 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 plus alpha k minus beta k vk equals the zero vector. But what do I know, and where can I go with this? Do you see why I'm so excited about this? v1 to vk are linearly independent. They're a basis. So in particular, they're linearly independent. So I have a bunch of coefficients, and I take this linear combination, I get equals 0. What do I have to know about all of those coefficients? Because it's zero, because it's a basis and therefore linearly independent. All of these things are 0. Or what does that say? Alpha 1 equals beta 1 dot 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 all the way up to alpha k equals beta k. So they were the same numbers, so we have a unique description. And this is what we want. If you have the basis which has these two properties of being able to span so that I can describe everybody, you can't ever get two ways, because as soon as you try to do it, you see that it was in fact the same way. So this is why we want a basis, to uniquely describe every vector in that vector space with just k guys. Now let's get into the notion specifically for Rn. What's the dimension of Rn? Well, n. Why is this? Let's get into the details. Okay, theorem for the vector space Rn, which is the set of all arithmetic column vectors. This basis specifically, which we call the canonical or standard basis of Rn, after we prove that it is a basis. So this set E1 consisting of a 1, basically E1 has a 1 in the first spot and zeros everywhere else. E2 has a 1 in the second spot and everywhere else. EI has a 1 in the ith spot, zeros everywhere else. This set of column vectors is in fact a basis of Rn. Then if you think about the previous theorems that we already did, we have an immediate corollary, or something that is an immediate consequence of the theorem, which says we know now that the dimension after my remark is the number of vectors in any basis, because those are all the same cardinalities. And if I have n of them here, that has to say that the dimension of Rn is in fact n, because this has n guys. Any other basis will also have to have n guys, and the dimension is the number of vectors in the basis. And B is a basis, and there's n guys in there. So the dimension of Rn is in fact n. This gets a lot weirder when I say, what is the dimension of, say, the set of all 3 by 3 matrices over the real numbers? This is 9 dimensional. You're like, what? That seems so weird to talk about 3 by 3 matrices and talk about dimension. You're thinking about this wrong again. I have to go back to, if you give me this weird set of objects which I claim is a vector space, I need to find a basis for that vector space. It turns out there will be 9 guys in the basis for that, and so the dimension is 9. The dimension is the number of vectors in any basis that you find. How do we prove this? Well, I'm going to prove the theorem, not the corollary. I just proved in words, in rhetoric, what the proof of this corollary was. So how do I prove the theorem? What do I have to do for B to be a basis? We just got 2 Pavlovian conditions. 1, it's linearly independent. And 2, it spans space. So those are the 2 things I have to check, and we will have, in fact, that it is a basis. Let's erase and do that. checking independence when we actually have to do this in practice. Independence is a zero condition, and 0 plus 0 and k times 0, the zeros never change. So that last column is much easier to check independence than spanning. And if you're in the Goldilocks land of n vectors in n space, it's if and only if, if and only if, if and only if basis span independence. So never check span if you don't have to. Mark, especially in his questions, will force you to so that you know what it is. But if you can get around it and you don't have to check span, don't do it. Always check independence. So what I have to do is, what is it going to be independence? For independence, I have to say we have E1 up to En, which are the vectors 1 and 0s up to 0s and then 1s. So those are the guys. And what I have to show is, if I get the fact that if I have alpha 1 E1 plus alpha 2 E2 plus dot 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 plus alpha n En equals the 0 vector, I have to show that alpha 1, alpha 2 up to alpha n are all 0. I have the unique trivial solution to this homogeneous system of equations. Do you see now? This is why I'm going to open it up. I wasn't going to do it here, but I am going to do it. In practice, this is how you get an augmented matrix and row reduction in REF to answer this type of question. E1 is this guy, plus alpha 2 times 0, 1, this guy, plus all the way to alpha n times this guy, equals the 0 vector. Now augment the matrix. That should be diagonal. Equals 0, 0. You see I have a homogeneous linear system. What does that say? Immediately, this says that I'm already in reduced row echelon form, because it was the identity matrix in this case. When you have a non-standard basis and you have more coordinates, you're going to actually have to row reduce to answer the question. But in this one, I get it immediately. What does this say? Do I have a row of zeros? How many solutions do I have? Again, now all of a sudden we're back in chapter 1, where I have to say I'm in reduced row echelon form, and I have how many unknown variables did I have? Alpha 1 to alpha n. And how many leading ones do I have? N. So I have a unique solution. What is the unique solution? The unique trivial solution. And this is exactly what I want. This says that alpha 1 has to equal 0 up to alpha n equals 0. So because I had a linear combination which equaled 0, the only way to get that is the unique trivial solution to this homogeneous system, which I did get. And that says by definition, E1 to En are linearly independent. By definition, good. It's never going to be that easy for you, because this was the standard basis that's already in our REF. When you have coordinates, you're going to have to row reduce and do this. We'll probably do an example later or in another video. Now what do I have to do? Make sure that I can describe everybody. This says if I can describe everybody and they actually do span, then it's going to be unique. But this is the Goldilocks land. If I have n of them and I'm in n space, it's if and only if. Why is that true? Well, it's going to look awfully similar. So now let's do the span question, and it's going to look identical to this, except what's going to happen? 0 becomes an x, and then I have to work with that scenario. So let's do that. Do E1 to En span Rn. What is this condition? This set of vectors spans Rn if and only if any vector I take in Rn implies we can write x as alpha 1 E1 plus dot 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 plus alpha n En. And I want to know right now if this is true. So that's where I put the question mark to say that's what I'm asking myself. That's not the deductive proof of it. So this is what I need. I have to take an arbitrary vector in Rn and write it as a linear combination of these guys, and this is why I really like this one. So take an arbitrary vector x in Rn. And now I'm just going to open up, and this is my favorite dirty trick. This is why it's called the standard basis, because it's so easy to describe every vector as a combination of these e guys. I'm going to use scalar multiplication in addition in reverse. This is actually equal to see where I'm going with it already now. Yeah. So what I did was I just split that single vector as the sum of n vectors. And now I can write 0, x1, 0, x1. So these all have an x1 in them. I can factor the x1 out of them. And this is going to be well, what is this? This guy is E1. Dot, 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 xn, en. So the coefficients you need are, in fact, the coordinates you already have for that vector. What does that say? Any vector I take in Rn, I can write as a linear combination of E1 to En. So this says that E1 to En span Rn. And if you have a set which spans Rn and is linearly independent, this says that E1 to En is a basis of Rn. Because there was n of them in there, and any other basis is also going to have exactly n. The dimension is the number of vectors in any basis, and in this case Rn has n basis vectors, so the dimension of Rn is n. Up and down and left and right and forwards and backwards seems like an obvious to call 3-space 3-dimensional, but when you get into weird ones like how can there be an infinite dimensional Banach space, well, we look at, you're phrasing it wrong, look at what the basis is of those continuous functions that are periodic. You're talking about Fourier series now. And then if you have those, then what's a basis for those periodic functions? It turns out Fourier magically and then kills himself with heat exhaustion. That's where he figures out systematically how to describe heat. He kills himself, he used to create these sauna rooms, and they basically killed himself over heat exhaustion. Irony. Is that irony? Yeah. No. Coincidental, unfortunate. You tell me in the comments if that was irony. My point being is, this space that he creates is infinite dimensional because if you take periodic continuous functions over an interval, the way to describe them is the basis is going to be cos nx and sine nx for every integer n. And how many of those basis vectors are there? Infinitely many of them, so we call that an infinite dimensional space. So whenever I'm talking about dimension, what you really have to do is figure out how to cleverly find a basis for that space, count how many things you have, and then it doesn't sound so grandiose to talk about an infinite dimensional vector space. We are not going to consider infinite dimensional vector spaces here. They'll be finite dimensional, and then later on in the course, once we get to the nitty-gritty, I can show you that every vector space which is finite dimensional, is isomorphic to some Rn for some integer n. They're all essentially different ways of viewing n-dimensional vector space. This guy, essentially up to each dimension, there's only one type of vector space, Rn. Let's do an example. You can tell the curvature of n-dimensional manifold regardless of whether the fact of the species could get off of that n-dimensional manifold. You don't have to be outside or in a higher dimension to tell what the curvature of the manifold is. So now if we're stuck in 3-space, we can still find out what the curvature of 3-space is without having to get outside of 3-space to look down upon it. Tour de force. Gauss did a few things. That Euclid guy's all right, he commented after he solved the Angon problem over 2,000 years. We're about to use Gaussian elimination now to answer the question. Now we're finally at the culmination of using day one stuff, row reduction and REF of a linear system to answer these horrible questions about, are these vectors a basis? Do they span? Are they independent? And now they're all swirled and related to each other. Independence says that if you write vectors as a linear combination equaling 0, all those coefficients have to be 0. Span says linear combination again. If you write those guys, every vector in the space as an arbitrary linear combination, then they span the space. If you have those two things, you're a basis. Now I'm going to do the horrible question which you should try and avoid at all times, but I'm going to force you at least once so you know what it is. Here's the sweat-producing question. Do these three vectors span R3? First of all, what does that mean? It means every vector I take in 3-space can be written as a linear combination of these three guys, and let's call this one just to match. This will be V1, V2, and V3. And in a second, we're going to do the 3 cases, and this is the anti-Goldilocks land of this vector spaces, of the magic land, where I'm given 3 vectors in 3-space. This could either be yes a basis or no a basis, we don't know. In the other 2 cases, if I'm given less vectors or more vectors, it's always a no, and we'll go over why. So here I genuinely have to check. What we're first wanting to know is the definition of span is going to be this. If I take any vector in R3, we need to, can I write x is equal alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. And what's going on here now is we have two sets of unknowns here. This guy has a set of unknowns. For simplicity, I'm going to call him A, B, C. Those are three unknowns. And now I'm actually trying to, also these are three unknowns. And I'm going to try and now row reduce this system and try to find out whether these three unknowns depend on those three unknowns. And that's a lot of unknowns going on, and then I have to augment the matrix and row reduce this and somehow decide whether I have one solution, no solution, or infinitely many solutions will tell me whether I have a yes or no to the answer. Do they span? Let me do it and then we'll recap at the end. So putting that coordinate in there, and then these guys all have their coordinates, I can create a 3x3 non-homogeneous system. What is that going to be? We classically write this as alpha 1, 1, negative 1, 3, plus alpha 2, negative 2, 2, negative 6. This is a multiple of this, and this is a multiple of this. So the dimension is 1. They definitely don't span, but if you hadn't noticed it, these are just multiples, so they're not linearly independent. Anyways, plus alpha 3 times 4, negative 4, 12 has to equal our arbitrary vector ABC. Now that's actually the definition of span. If I can take an arbitrary vector and write as a combination, this is what I want to know, but I still don't know. How am I going to tell? Now we're going to augment this matrix, row reduce, and try to find out. So what is the augmented matrix? The augmented matrix is 1, negative 1, 3, negative 2, 2, negative 6, 4, negative 4, 12 equals A, B, C. Now I have an augmented matrix. Now this is where I switch knobs in my brain. First I had to do what the heck is spanning, so I fleshed that out. Now I'm ignoring entirely what spanning or anything means. Switch to chapter 1. I need to augment it Pavlovianly, augment the matrix, row reduce to REF, and decide whether I have one solution, no solution, infinitely many. Then I'll switch back to answering the binary question of yes or no to span. So right now I don't care about any of this. I'm just, here's a matrix, I need to augment it. Gauss's mantra says what? I have a leading 1 in the top left corner and kill below. Eliminate those variables. So I'm going to do row 2 goes to row 2 plus row 1, and row 3 goes to row 3 minus 3 row 1. When I do that, what am I going to get? I'm going to get 1, negative 2, 4a, which never changed. I know what's going to go on here, so I'm going to leave myself a little bit more room in there. And then now I'm just adding, so negative 1 plus 1 is 0. Negative 2 plus 0, 0. And then what is this? B minus A. I know this is why. Would you like those to be zeros? The independence question is much nicer because they never change. You'll see in a second when we get there. Now I'm going to do negative 3. What's going to happen? 3 minus 3 is 0. Negative 6 plus 6 is 0. 12 minus 12 is 0. Oh, we got goose eggs again. But now what do I have? C minus 3A. So now what do I have to do? This is REF. I have to say, is this REF? Yes. Do I have any leading ones? Yes. Are there zeros below? Yes. Are any of the leading 1 entries further to the left? Yeah. So we have our business. Now what do I do with this? Why does this tell me no, they don't span? Because I needed every arbitrary vector ABC to be written as a combination. But if you get this, when is this system consistent? When does this system have at least one solution? It can't have a unique solution, can it? Because it doesn't have the 3 leading ones. So for this to be consistent, I only have 2 options left. It can't be a unique solution, so I'm going to throw that one away in this scenario. So now I only have 2 choices. Either it has infinitely many solutions and is consistent, or it has no solutions and it's inconsistent. If it's inconsistent, that means I can't write some of the vectors as that, so I don't want inconsistency. But in this scenario, when am I going to get consistency? This is consistent, so has infinitely many solutions. If and only if what? This has to be 0 and this has to be 0 to get rows of zeros. Otherwise this says non-zero equals 0, which is a contradiction. So the only way I can have that is if b minus a equals 0 and if c minus 3a equals 0. And if you rearrange that a little bit, what that says is a has to equal b and c has to equal 3a. And again, why is that? No to span. So just a second. What that now says for me is from here, that says if I take an arbitrary vector A, B, C, can I write it in the span of these three vectors? It turns out no, because these were multiples of each other. It's only if they're going to look like this. That says now what? This says A had to equal B, and C had to equal 3A. So the only way, am I missing a negative somewhere? Yes, because that was this one was a plus. Oh, got the negative B. I saw it immediately because it was like, and so did my cameraman. I could tell. It was like something, how can, yeah, do you see now? Which is what? Only if you're a multiple of that vector can you be written as a multiple of that vector, it turns out. So, what's the moral? For now, because you're shell-shocked, what's the condition? If you get conditions on the coefficients, that means not every vector, willy-nilly vector in the 3 space can be written as a combination of these 3 guys. Only if they're a multiple of this vector, which these 2 also are, can you write them as a multiple. So if you get conditions, that says not every vector's in the span of those guys, only guys that look like this. And so this says not spanning. So no, they don't span. And how do I do that again? This is an extremely clever but convoluted process. I take the vectors, I line them up into a system, I augment the system, I get to REF. Once I get to REF, I either answer a yes or no condition to when I'm going to have yes span or no span. In general, if you have a choice of doing span or independence, what's the span going to look like? This hot mass. What's independence going to look like? This, because the zeros never change. And now what does that say? Because we're about to do the Goldilocks land. If I'd said, are these independent? It's also a no. Why? Because I would set this up instead of making my vectors equal that arbitrary vector, they have to equal the 0 vector. Then I augment and row reduce, and what does this say? I have infinitely many solutions, don't I? Because I'm in REF. Is that the unique trivial solution? No. And independence says you're independent if and only if you have this gives you the unique trivial solution, which I didn't get, so these are not independent either. And this is what the Goldilocks land is going to say. If you have 3 vectors in 3 space, it's yes, they're independent, if and only if yes, they span, if and only if yes, they're a basis, or no, they don't span, if and only if no, they're not independent, and then therefore, if and only if no, they're not a basis. So let's go through those 3 cases. What are the 3 cases? I can give you 2 vectors in 3 space. I can give you 4 vectors in 3 space, or I can give you 3 vectors in 3 space. I gave you 17 vectors in 3 space also. But if I've given you less vectors than the dimension you're in, the same number of vectors than the dimension you're in, or more vectors than the dimension you're in. Remember, the dimension I'm in is the number of coordinates. The number of vectors I have is k. Let's do the demographic of linear independence and span in dimension n. All right, to finish off, I think that's roughly all I have to say about it for today anyways. I have a little bit more, but that was the minimum amount I could talk about linear independence, span, dimension, and basis of an n-dimensional vector space. Here's the demographic now of independence, span, and basis. There's 3 cases that a lot of people don't think about, so when you're doing this, if you don't think about this, this is how the questions will trick you and get you. Spanning and independence are not the same thing, otherwise we would just have one horrible definition, not 2. But they are the same thing in anti-Goldilocks land. They're not the same notion in these ones. So let's go over what I'm talking about. If k is going to be the number of vectors I have, let's do v1 to vk. So I have a set of k vectors. We now know that k has to be n if it ever hopes to be a basis for n dimensions. But let's go through this. There could be 3 cases. The number of vectors I'm given is less than the dimension I'm in. Remember, the dimension is the number of the coordinates of each vector. So each of those vectors is going to have n coordinates. That tells me that I'm in Rn. The number I have is just the number k, the number of vectors I'm given. So if I'm given less vectors than the dimension I'm in, they can never span all of that space. And because they can never span all of that space, I need a basis to be independent and span. And because one of the conditions has already failed, if I'm looking for mammals, and mammals are warm-blooded and produce milk and give internal gestation and have hair, there's non-placental and placental mammals now because of the echidna and the platypus, but whatever. If I'm looking and I grab a lizard and I say, "Are you a mammal?" My analogy here also is extremely poignant because one of the conditions is easier to check than the others. A mammal, or the lizard, is cold-blooded and I want warm-blooded. Do you know how to check warm-bloodedness of a creature? Me neither. That one's, it's like, it's supposed to be, but I don't know actually how to check warm-bloodedness. But it's also supposed to have hair, and the lizard I can immediately check and he's like, oh, he's got no hair. So one of the things failed, even though if I don't know how to check the more complicated version of cold-blooded, I'm no longer concerned about cold-bloodedness, because if it had hair then I would have to check cold-bloodedness. But because it already doesn't have hair, I know that lizard is not a mammal. So I want to check the easiest condition. My point being in that analogy is as soon as one of the conditions fails, you're not a mammal anymore. You have to have all 4 conditions to be a mammal, placental mammal. Otherwise, you're not going to be a mammal. So if I'm worried about those, try to, as soon as one fails, you can't be a basis or a mammal. So spanning is the harder condition to check. So try to find independence first. Try to see that it has no hair, then check that it's warm-blooded first. So in this scenario, I can never span, which is the horrible condition. So it's never going to be warm-blooded, so it's going to be not a mammal. So in this case, if I like to pick 2 dimensions. Think about the plane. We know that the plane, any 2 non-collinear vectors is a basis. So if I'm only ever given 1 vector in 2 space, that single vector can never span all of space, and therefore that set of vectors can never be a basis for that space. So if you have less vectors than the dimension you're in, you can wave a hand now at this board and say, you showed in one of the lectures that if I have less vectors than the dimension in, I can never span, and therefore I'm not a basis. If I go, I'm going to skip anti-Goldilocks land for a second, then go to the other extreme. These are the 2 easy cases. It's an immediate. If I give you more vectors than the dimension I'm in, now I'm going to give myself specifically, this is the canonical basis of R2. So if I was just given those 2 guys, which I did in this case, yeah, a basis for sure. But now if I add another vector in there, does it wreck spanning? No, not really, because if I add that other vector, I could just use the clever 0 coefficient. And so if I could describe everybody with these guys, adding that vector in there, I can just use him as a 0 coefficient. That's not going to ruin describing everybody. What does it do though? You can clearly see that this vector is this one plus this one. So hopefully you can see that. This vector depends on these guys, doesn't he? So if I'm given 3 vectors in 2 space, they can never be linearly independent. One of them will always depend on another. So because they're not independent, not a basis. So if you're given less vectors or more vectors than the dimension you're in, the number of coordinates you have, you can immediately just wave a hand at saying this is not a basis. But you can have that if you're given less vectors, this vector is linearly independent of itself. There's only one. So any vector is linearly independent of itself. So this vector, or this set, is linearly independent in R2. It spans a line, but not all of space. So it doesn't span. So this is where you can't just conclude it's also not linearly independent. This vector is linearly independent, but not spanning. These vectors are not linearly independent, but definitely do span 2 space. So it's not the same condition, but in anti-Goldilocks land it is, or I don't even know if it is anti-Goldilocks land. Just because you get 3, I call it anti-Goldilocks land because not every 3 vectors is going to be a basis, but the only chance you ever have of hoping to have a basis is in the Goldilocks land where I have 3 vectors in 3 space, or 4 vectors in 4 space, or 10 vectors in 10 space, which is apparently what we're in. We can only perceive 3. I need 10 basis vectors. Where's the direction orthogonal to the first 3 directions? Up, down, left, right, forward, backwards. Nope. So yes, abstractly, we need another dimension to go perpendicular to the rest of these, and we don't know how to do this. But abstractly, if I'm in 4 space, the only hope that I can have to have a basis for 4 space is 4 vectors. But I point out it's a theorem. Given n vectors in Rn, you're independent if and only if you span, if and only ever a basis. So it's 3 yeses or 3 nos. This is 2 vectors in 2 space. They're the canonical standard basis of this. So yes, they're independent. Yes, they span. And therefore, yes, they're a basis. This one is just a multiple of this one, but it's still 2 vectors in 2 space. So I have to check. No, they're not independent. No, they don't span. And no, they're not a basis. So it's either yes, 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 or no, no, no. This is the scenario of how to decide whether something's a basis. Span and independence are not the same condition. You can be independent and not span, but only if the number of vectors you have is less than the dimension you're in. You can be spanning, but not independent, but if and only if you're given more vectors than the dimension you're in, and not if and only if. And then in the Goldilocks land, you're given n vectors in n space, you're a basis if and only if you span, if and only if you're independent. And because it's an if and only if now, checking warm-bloodedness is crazy, and checking whether it has hair seems relatively easy. So independence is really easy to check because it's a zero condition, and spanning, you just saw by the example I did, you're like, I don't know like what's going on. So if you get Goldilocks land where you get n vectors in n space, why would you ever check spanning again? It's if and only if. So even if I ask you the question, do these three vectors span space, I can check independence. And then if I get yes to independence, I can say yes to span because my theorem says if and only if. You see what's going on there. If you didn't rewind and meditate, I'm out of here. Please subscribe right there. I'll see you next time.